Hi, Math 243 students. We are now starting section 5.1, where we're going to talk about continuous probability functions. I dropped my pen. All right, so last section we talked about discrete probability distributions. So this was an example of a discrete distribution. We roll a die one time, record the number, and we're going to repeat this experiment 1,000 times. All right. The data from this experiment is quantitative data, but it's discrete. You're going to have the number one, the number two, et cetera, six. You can't have 1.5, you can't have 3.1, right? Just those six numbers, and that's it. If we made a histogram of the data, I guess this is a histogram of rolling a die 500 times, it would look like this. Here's my ones, my twos, my threes, my fours, my fives, and my sixes. It's about averaging out to about, 80 each or whatever that number turns out to be. So that's a discrete probability distribution function. About 1/6 of the time, you get each of those individual numbers. What happens if we have more continuous data? So let's suppose we're studying the data of a heating cooling company that records the lengths of their visits to customers. So the lengths of the visit could be anywhere between an hour and 6 hours. So this data is quantitative, but it's continuous. You could have 1.15 hours or 5.3 hours, right? It's not whole numbers. And we're not talking about like billing hours or something here. We're literally just talking about how long did it take them to finish the project they were working on for their customer. If we made a data of this, it might look something like this. And these all have bins. And here's my one at the edge. This is going to be 1 to something, 1.2 or something. And up here is my last bin. And this goes up to 6. I don't know, 5.8 to 6. I don't remember what the bin widths were. But right, no matter how many bins we have, there's going to be in between values because we're having any value between 1 and 6. This is the interval 1 to 6 and anything in between. Okay. And actually, I should have square brackets on this to be more clear. 1 to 6 and anything in between. Okay. That's what we're talking about when we talk about continuous probability functions. It's going to be a probability function that the data values can take on any value in a range. Let's look at the difference between these two. On the discrete probability distribution functions, the data is discrete particular values. On the continuous distributions, it's any number between a range. So no matter what we do in the discrete ones, we're only going to get 1, 2, 3, 4, 5, or 6. That's our options. On the continuous, we can have any number between 1 and 6. For discrete functions, the probability of getting a 1 or a 2, since this is evenly distributed, each of those is 1 in 6. For the continuous probability distribution function, the probability of any one particular value is actually going to be 0. And the reason that is there's infinitely many choices of values between 1 and 6. So the probability of hitting one of those values is 0 because we have infinitely many choices. So to measure our probability in continuous functions, we measure an interval of area. So instead of saying what's the probability of 1, we might say what's the probability of being between 1 hour and 1.2 hours. For this to work, in discrete, we count for the probability. How many times did the 1 happen out of the total 500 times, right? And in continuous, we measure an area for the probability. We actually calculate an area under the graph there. All right, so let's go through an example of a continuous probability distribution function. I lied. Let's not do an example. I need to talk about some more things first. All right, so the graph of a continuous probability distribution is a curve, and the probability is represented by area under the curve. That curve is called the probability density function. We're going to refer to as f of x because it's a function, and that's what we use for functions. And we're going to use the function to draw a graph of the probability distribution. Again, a couple more items. This is a lot of information, but I'm going to go through some examples, and it should be straightforward after the examples. Remember, the outcomes are going to be measured as area, not counted up. And the area under the curve and above the x-axis for the entire curve is going to be equal to 1 because something in that distribution has to happen. These other ones I'm going to skip over for now, and I will do them in the context of an example. So the example I'm going to do is the uniform distribution. We're going to talk about two continuous distributions in this class. The uniform one is not as useful in the real world, but it is a very good one to practice with and get used to the vocabulary and calculations. The one that's really useful in the real world is a normal distribution, and that's the one we're going to talk about next once we get a little bit of the hang of this. All right, so let's start with an example. The amount of time in minutes that a person must wait for a bus is uniformly distributed between 0 and 20 minutes. So that means that any value between 0 and 20 minutes is as likely as any other value. So the probability distribution function for this is f of x equals 1 over 20. And if we were going to draw a graph of that, it would just be a horizontal line at 1/20th. It would look just like my graph here. From x equals 0 to 20, and then it stops, right? Here's my graph of my function. And each value represents a wait time between 0 and 20 minutes. So this is the first example we're going to talk about. If we wanted to compute the probability that the wait time is between 0 and 20, so what's the probability that you have to wait between 0 and 20 minutes? We would compute the area under the curve starting at 0 and ending at 20. Well, that's this area. And we know how to find the area of a rectangle. It's base times height. The base of the rectangle is going to be this length, which we know is 20. We calculate that it's 20 minus 0, so 20. The height is 1/20th. And if we multiply 20 by 1/20th, we get 1. And this is a really good thing because just like in discrete distributions where all the probabilities had to add up to 1, in continuous distributions, the area of the entire possible values better add up to 1 as well. So my entire area over the x values better add up to 1 because one of these things has to happen. The bus has to arrive between 0 and 20 minutes somewhere. All right, so let's suppose using this uniform probability distribution, we want to find the probability that the wait for the bus is going to be 2 minutes or less. Remember, we're going to calculate area for continuous distributions. So we want to know that the probability is between 0 and 2. So the area is going to be this purple box. The width of my box or the base is going to be width base 2. The height is 1/20th. So the area of the purple box is 0.1. That area is a probability of the wait time being between 0 and minutes and 2 minutes. So we wanted using math, we would say the probability that x is between 0 and 2, or in this case, just that x is less than 2, because you can't be less than 0 for wait times, is equal to 1/10. Right? So again, our area is going to correspond to our probability. Let's go ahead and have you try one. I would like you to find the probability that the wait time is between 4 and 15 minutes. Pause the video and give it a try. All right, are you back? Well, we need to find the area of my purple box here, right? The base of the box is going to be this length, which is 15 minus 4 wide. The height is 1/20th. And so the area is 15 minus 4 equals 11. I guess I didn't finish writing this. That's my base, my rectangle. That's 11. The height is equal to 1 over 20. 1 over 20 times 11 is equal to 0.55. So 55% chance that the probability that the wait time is going to be in between 4 and 15 minutes. So if we wanted to write that mathematically, I bumped the screen, sorry. The probability that 4 is less than x is less than 15 equals 0.55. That's I like to think of it as like that purple box is 55% of the area out of the entire box from 0 to 20, right? That is 55% of the time you're going to wait between 4 and 15 minutes. All right, so let's go ahead and practice a little bit with our notation. The probability density function is going to be equal to f of x equals 1 over b minus a for a less than or equal to b, x less than or equal to b. This is a lot of a's and b's, but if we think about it in our example, what did I do here? Yikes. In our example, right, a was equal to 0 and b was equal to 20, right? So our example had f of x equals 1/20th. That was our height for 0 less than or equal to x less than or equal to 20. So that's how we relate to our example. A is your lower value of the uniform distribution and b is your upper value. The notation we use as the random variable x is distributed as uniform A, B. So it tells us the least and the most. A is the lowest, B is the highest. For this value, we know that the mean is going to be A plus B over 2, which makes sense. That's the average value between A and B. And the standard deviation is equal to the square root of B minus A squared over 12. I'm not going to go through where those formulas come from because that's really beyond the scope of this class. So let's go back to our bus example. We know that for our bus example, our random variable distributed uniform 0, 20. And so our probability density function, f of x, is equal to 1 over 20 for 0 less than x less than 20. What is going to be our expected wait time? Well, we plug in and average the values between 0 and 20. We get 10 minutes. It's our expected wait time. All right, let's try another example just to get a feel for this uniform. The data below are 55 smiling times in seconds of an 8-week-old baby. The sample mean, so if we just took these values and found the mean, it's 11.49. And if we calculated the sample standard deviation, like we learned how to calculate using Excel, we would get 6.23. We're going to assume, I'm going to tell you, that this is distributed uniform 1 to 23. So that means that any smiling time between 1 second and 23 seconds is equally likely. The way I'm telling you this, but what you would do is you would look at a histogram of the data and decide if you think it looks like uniform distribution. Is it flat across the top like that? This is what you would do. We don't quite have enough data to really make that work. All right, so our random variable is the length in seconds of an 8-week-old baby's smile, and we know x is distributed uniform 1 to 23. What is our probability density function for this example? Well, for this example, our a value is equal to 1. Our b value is equal to 23. So f of x equals 1 over b minus a, 1 over 22, for a, or 1, is less than or equal to x is less than or equal to 23. If we graph that using just a graphing calculator, I use Desmos here, we see that it starts at 1, it ends at 23, and the value here is going to be 1 over 22. I didn't label it as well as I should have, but that value is at 1 over 22. That means any time between 1 second and 23 seconds are equally likely. Let's using this same distribution that we've been talking about, what is the probability that a baby's smile will last between 16 and 18 seconds? And remember, this is the probability that 16 is less than x is less than 18. And remember, in continuous distributions, probability equals area. So what we're talking about is the area under the curve here between 16 and 18 seconds. Well, again, that's just a rectangle, right? So the base of this rectangle is 18 minus 16, that's 2. That's here. The height of the rectangle is 1/22, because remember that was our probability distribution function. 2 times 1/22 is 1 chance in 11. So the probability that the smile is between 16 and 18 seconds. Oops, I didn't mean less than or equal to. Equals 1 chance in 11. All right, so we can even put that as a number if that makes us feel better. I grab my calculator here. 1 divided by 11 equals 0.091, about. So about 9.1% of the time, the smile will be between 16 and 18 seconds. When I wrote just a few minutes ago, I had written down a less than or equal to and a less than or equal to and 18. But if I do put in less than or equal to, it actually doesn't change the probability. And the reason that is because if we include the endpoints, right? If we include this, oh man, I bumped that again. If we include this endpoint 18 here, right? The width here does not have any width. There's no width at a single point. So if I wanted to find the area of this little teeny red rectangle, well, it's not a rectangle. It's only a line. It has no width. So that has area 0. So adding the equal sign or the less than or equal to sign to the less than doesn't make any difference, because no individual point has any probability. Remember, I said the probability of any point is 0. And that's because we can't have an area at a single point. There is no width. So you can include the less than or equal to, or you can just put less than, and it's not going to affect the probability. Let's see if we can figure out the expected smile time for this distribution and the standard deviation. Well, remember, A is 1 and B is 23. So we find the average of those values, and we get the average expected smile time, 12 seconds. Using our formula for standard deviation, we got 1.354 seconds. And actually, if we look back at our sample, the sample mean is actually pretty close. Our standard deviation isn't that close, but that's okay. We'll come back and talk about that another time. So that was the standard, and that was the uniform distribution. It's always going to look like a rectangle. It has every value equally likely, so there's no up and down. It's always equal to the same value. Remember that the probability is the area of this square that you're interested in. So that's one type of a continuous probability distribution, the uniform distribution. The next one we're going to talk about is the normal distribution, but that's the next section.